Before I move on to the next question, just now recall that I mentioned to you when finding the gradient of a line that starts from the origin, the value is the same as that of a single point substitution, as when a single point substitution is used. Then I give you the example of taking this point here for your single point substitution, which in turn gave you the same answer as the gradient from the origin, right? What if you took another different point, say maybe this point here instead? Would you still get the same answer as this? You are still going to get the same answer. Let me show you. If E is equals to stress over strain, this value of stress here is 1 times 10 power 6. This value of this value of stress here is 1 times 10 power 6. This value of strain here is 0.5 divided by 100. It will be 1 times 10 power 6 divided by 0.5 divided by 100. You're going to get 2 times 10 power 8 Newton per meter square. It's going to be the same. Okay. So if you notice that the line, whatever you're trying to find is actually the gradient from the origin, okay, it will be the same as just you taking a single point substitution at any point. Okay. So maybe I try to write something here. You can finding gradient of a straight line. Okay, become more specific here. And finding gradient of a straight line that starts from origin, the value is the same as when single point substitution is used for any point on the line. Okay, this is something I want to add in addition to what I wrote earlier. Okay, so just bear this in mind. When it comes to current electricity, 3 chapters from now, we will revisit something similar again. Right now, it's not that important to know this, but it's useful. Okay, so if nothing else, then we move on to the next page, which is page 6. Okay, right, this one is your structured questions. I'll clear everything off. Okay, now a spring is kept horizontal by attaching it to points A and B as shown in figure 4.1. Point A is a movable slider, and point B is on a fixed support. Point A can move, point B is fixed. A car of mass 1.7 kg has horizontal velocity v towards the slider. The cart collides with the slider. The spring is then compressed as the cart comes to rest. The variation of the compression x of the spring with force F exerted on the spring is as shown here. Now, figure 4.2 shows the compression of the spring for x 1.4 force 1.5 Newton to 4.5 Newton. The cart comes to rest when the force is 4.5 Newton. Now, show that the compression of the spring obeys Hooke's law. Okay. Now, they want you to prove that the spring obeys Hooke's law. If you had just said that the line is straight, therefore it obeys Hooke's law, this one is wrong. Okay. If you say that because you see that right now the line is straight, then you say that because the line is straight, it obeys Hooke's law, and then you put this as your answer, this one will be considered as wrong. Because recall something earlier I mentioned to you guys before, Hooke's law is F equals to Kx. F is directly proportional to X. Okay, F is directly proportional to X. Okay, the keyword here is directly proportional. If it is directly proportional, that would mean that you have a straight line graph that passes through origin in fx graph. Okay, so what it means is that you are supposed to see something like this for force versus extension graph, like this. This one is what we say Hooke's law obeyed. Okay, and this is Hooke's law obeyed, because you can see that it clearly starts from 0, the origin. Okay, right. This one is 0, this one is 0. All right. If you had something like this instead, and let me redraw something else for you. Okay, I tried to use back the same graph to save space. If you see something like this, this is Hooke's law obeyed. But what if you have another separate line? I mean, if you plot a force versus extension graph, you also get a straight line, but it looks like this. Does this mean that, so this line is also a straight line. And this line is also a straight line, just like the red line here. But does this mean that Hooke's law is obeyed? Okay, so this one here, the green line, Hooke's law is not obeyed. Okay, because F is not directly proportional to X. Okay, so the thing here is Hooke's law specifically says that force is directly proportional to X. That means that in the force versus extension graph, it has to pass through origin. Okay, if you have a graph which is also a straight line, like the ones that you see here, but it doesn't pass through origin, that one is not obeying Hooke's law. Because if it's like that, it doesn't mean that F is directly proportional to X. Okay, just because it's a straight line does not necessarily mean that Hooke's law is obeyed. Okay, maybe I better just write it as a remark here. Okay. Just because line is straight does not mean Hooke's law is obeyed. It must pass through origin. Okay, that is the statement here. Maybe I highlight it so that it's easier for you guys to see. Okay, just because the line is straight does not mean Hooke's law is obeyed. It must pass through origin. Okay, so now when you look at this graph here, notice that the axis is not showing 0. How do you know this straight line? This straight line passes origin. Just by looking at the graph like this, yeah, you know it's a straight line, but how do you know that it passes through origin? You don't know, right? So right now, when they ask you to show that the compression of the spring obeys Hooke's law, in the first place, if you say that the line is straight, it obeys Hooke's law, this one is really wrong in the first place. So rather than saying something here like this, you can prove that line passes through origin. And this one, if you prove that the line passes through origin as your answer, then this one will be considered as correct. So what do I mean by proving that the line passes through origin? There are some workings here. I will just show it to you first. Okay, there's one way of doing this. This one I think is already obscure. Okay, this one let me just show it here. How do you prove that the line passes through origin? Okay, so this one is the working. The answer is this one. And this one is the answer. This is the actual answer. Okay, so what you want to do is that if it's a straight line that passes through origin, let me get this. If you know there should be a straight line that passes through origin, the equation of the line would be y equals to mx. I mean, it should be y equals to mx plus c, but because if passing through origin, then y is equals to mx itself. Okay. Right. It's a straight line passing through origin. The general equation should be this. Okay, prove that the line passes through origin by showing that it is in the form of y equals to mx. Okay, how do you prove that the graph passes through origin? You show that the equation of this line is in the form of y equals to mx. So what do you do now is that firstly, you can find the gradient. Okay, the gradient here, I'm just going to use by the values that I have here. Okay, but because this is obscure, I'm just going to use the gradient I have here. This one is 4.5 minus 1.5 divided by 1.8 minus 0.6, giving you 2.5 Newton per meter. Okay, then after I tell you taking point 0.6 and 1.5 and substituting into y equals to mx plus c, you get 1.5 equals to 2.5 times 0.6 plus c. So c is 0. Okay, up to this part, you should understand, right? In maths, if you're asked to find the equation of a line, this is generally what you do. This is you actually finding equation of a line. Okay, in maths, you learned this before. You need to find the gradient. You need to first find m and then substitute into y equals to mx plus c to find c. Isn't it? This is what you did last time in maths. When you want to find equation of a line, you find the gradient. Then you sub it into y equals to mx plus c to find c, which is what you're doing here right now. Okay, in this working here. So you find the gradient, you take one point, sub it into y equals to mx plus c, then you find out the c. So then after that, from here, you see that, therefore, f is equals to 2.5 x. Okay, folks, this one f is equals to 2.5 x. Force is directly proportional to extension. Therefore, Hooke's law is obeyed. Okay. This one here, you already proved that is the same as y equals to mx So it's directly proportional. It passes through the origin. Okay, this one here already means that no y-intercept passes through origin. Okay, this is one answer to prove that it passes, that this one obeys Hooke's law. So you just write that it's a straight line, therefore obey Hooke's law. That one is actually not really that accurate. You have to prove that it passes through origin. You have to prove that force is directly proportional to extension. This is what the method is supposed to be. Okay, this entire thing is actually the working. Okay, there's also another way to prove that Hooke's law is obeyed. I will show you two different ways. Okay, now basically if Hooke's law is obeyed, okay, this one is a bit messy already, so I'm just gonna clear off everything here and show you a different method of finding and prove that Hooke's law is obeyed here. Okay, so later on you can actually refer back to the recording if you haven't managed to finish copying everything. So I'll just clear this one first. There's another way to find out whether this equation obeys Hooke's law. This one may be easier to understand. Okay, now if force versus extension, you want to say that the spring obeys Hooke's law, it must pass through origin. That much you know already because of what I explained. Now, if you want to prove that it obeys Hooke's law, what you can do is that this one here is x1, this one here is f1, and then this one here is x2, this one here is f2. Basically, if Hooke's law is obeyed, K is constant, meaning K1 equals to F1 x1 should be equal to K2 F2 over x2. Okay, so if you have a graph for force versus extension, it obeys Hooke's law. Yes, you understand that it must pass through origin. One thing here that you could also say is that because you see it's a straight line, K it will be constant. Okay, K is constant, meaning to say K1 equal to F1 over X1 should be equals to K2 F2 over X2. All right, so what you want to do now here is that if you want to prove that this thing obeys Hooke's law, you can actually try to find the spin constants at the different points, which is actually this part here lah. Actually, yeah, this one. This is the other working. This is the second working. Find out the one value of spin constant from one point. Find out the value of spin constant from another point. Since those two are constant, therefore Hooke's law is obeyed. Okay, so this is another one. Some people may understand this method better compared to the first one, but I just tell you both at the same time. Okay. So maybe I give you a minute to copy this, then I'll do that before I move on. All right. Okay, so this one is okay, then I should move on to the next part. Okay, the subsequent part should be much easier. Okay, it's just that this part I may need to explain a bit more, but you get the idea now, okay? So you are basically trying to prove that the line passes through the origin, so that force is directly proportional to extension, okay? Or you're trying to prove the effect of force being directly proportional to extension, which is this one here, okay? So part one is okay. Then I move on to part two. Determine the spring constant of the spring. Okay, now determine spring constant of the spring. This one should be okay for you. There are two different ways here, as I mentioned to you. This one here is either you just find gradient itself, or you use single point substitution. Okay, or you use single point substitution. Okay, both are acceptable. It doesn't matter which one you use. So that's why I mentioned to you just now. Sometimes you may see me using gradient, but then when you check the marking scheme, they don't seem to be using gradient. They seem to be using just a single point substitution. If you know there is a straight line graph that passes through the origin, finding the gradient is the same as just you using single point substitution. Okay, so you will eventually find out the gradient as so you will eventually find out the spring constant as just being equals to 250 Newton per meter. Simple as that. Okay, so this part is okay. Then after that, determine the elastic potential energy stored in the spring due to the card being brought to rest. Okay, so elastic potential energy just now, as I mentioned to you last week, is known as your strain energy too. Okay, elastic potential energy is known as your strain energy. So they want you to find out what is the amount of EPE or strain energy stored in the spring due to the car being brought to rest. So if you recall back how the situation was just now, the cart, maybe I rub off everything. The cart was moving, it hits A. So as the cart hits A, it will compress the spring and then it will push A inwards. A will be pushed all the way in here. So as the cart pushes against the spring, it compresses the spring, but then at the same time, the cart will start to slow down. Because what happens here is that the KE is converted to EPE. Okay, the cart slows down, so the amount of KE that is lost is converted to EPE stored inside the spring. Okay, so KE is converted to EPE. KE of cart is converted to EPE of spring. Okay, so the cart will start to slow down to a stop when the force on the spring is equals to 4.5 Newton. I believe they wrote it somewhere here. Yeah, they told you that the cart comes to rest when F is equals to 4.5 Newton. Okay, so the cart will come to rest when the force is 4.5 Newton. So what you want to do now is to find out what is the amount of elastic potential energy that has been stored there. So you find out the area under the graph. So when you want to find out the area under the graph, you can try to visualize something like this. You already proven that force extension graph here is a straight line graph that passes through origin. So your cart stops when the force is 4.5. And then when the force is 4.5, the extension is 1.8. Sorry, compression is 1.8 millimeter, if I'm not mistaken. Sorry, 1.8 centimeter. Okay, so you want to find out the EPE is actually just going to be the area under this force extension graph. So just find the area. EP is area under the graph, half Fx, half 4.5 times 1.8 centimeter change to meter, you're gonna get this. Or you can also do it as this. EP is half kx squared. You already found out the spring constant is 250. So just sub it inside, sub in the compression, and you get the answer. Okay. So because this is still your graph obeying Hooke's law, that's why you can say that EPE is half Fx, half kx squared. So I made special mention of this in the previous lesson. Only applicable if Hooke's law is still obeyed. So this one is a straight line, Hooke's law, straight line through origin. Hooke's law is obeyed, so I can use this too. Okay. Then I go all the way. Right, so this part is okay. Again, 0.0405 joules. Okay, then the next one, calculate the speed of the card as it makes contact with the slider. Assume that all the kinetic energy of the card is converted to elastic potential energy of the spring. So earlier I mentioned that your card makes contact with the spring. Let me just clear off everything. This is getting. So earlier just now I made mention that when your card makes contact with the spring, it compresses the spring and then the card will slow down to a stop, right? So the KE of spring, sorry, the KE of card was converted to EPE of spring. So whatever KE is lost is equal to the gain in EPE. So loss in KE of card is equals to the gain in EPE of spring. Okay. They already told you specifically to assume that all the kinetic energy of the card is converted to elastic potential energy. You don't really need to bother about whether there's any effects of friction, since they already gave you this statement here. Okay. So your change in KE should just be half mv square. This one is actually half mv square minus 0. Okay, because as I mentioned to you just now, I need to scroll here and there. Your V is this part here. Okay, it's a bit slow, sorry. Your V is this part here. When your card makes contact with the spring, it will push the spring inwards. So your point A is now here. So your card will push your spring while it slows down. So it slows down to a stop. Eventually, it will reach a velocity equals to 0. So this part here is where your KE is half mv square. This part here is where your KE is 0. Okay. That's why my change in KE is equals to half mv square minus 0. Okay. So let's go through that. So it says half mv square minus 0 equals to 0.405 joules. I did not put the 0 inside because I omitted it out, but just know that it's minus 0 lah. So eventually you just submit all the values. Your mass is actually 1.7 kg. Your EP is 0.0405 joules. V is going to be 0.218 meter per second. This is your final answer. Okay, so this part is okay, right? Yeah, this is actually referring to conservation of energy. Okay, so this one is okay. Then I'll move on to the next part, which is this. Okay, the next part will be June 2015 P23, the next page. Explain how a series of readings of the quantities given in figure 4.1 is used to determine the Young's modulus of the metal. Okay, this one I forgot to write the question number. Let me just see. June 15 P23, right? Okay. June 15 P23 refers to which question? It refers to question 4. My mistake. The one that you see here in the next page, June 15 P23 refers to question 4, part B. Okay. Explain how a series of readings of the quantities given in figure 4.1 is used to determine the Young's modulus of the metal. A numerical answer of E is not required. Okay, this one is actually referring to this question. Okay. So they tell you, because you see this one is referring to what is given in figure 4.1, but your question didn't give you what it was. Okay. The figure 4.1 is this one. Okay. Figure 4.1 shows the values obtained in an experiment to determine Young's modulus of a metal in the form of a wire. They give you the diameter, the length, the force, and the extension. And these were the values. And then they ask you to state the instrument that you could use to determine the values of these quantities. Okay, so that's what part B in your worksheet is saying now. Explain how a series of these readings that you have here can be used to determine Young's modulus of metal. A numerical answer for E is not required. Now this part here is actually referring to measurements that you take to determine E, which is in turn related to this equation. Okay, this experiment to determine E, we've learned it inside your notes already. It's under page 7, this one here. Okay, so as mentioned to you, since Young's modulus is stress over strain, and then stress is force over area, strain is E over length, E is FL over AE. So after that, what you do is that force is equals to EA over L times E, which is actually the same as the equation of a straight line. You should get a straight line through origin, okay, which is what you see here. The gradient will be EA over L, which if you expand further, area is pi over 4d squared. Okay, so what you want to do is that how would you use the readings that you have in the figure 4.1 to find out the Young's modulus of the metal? Why do you take a few readings? Meaning to say, why would you take F1 and then find E1, F2 and then E2, F3 and then E3 to find Young's modulus of steel? It's because you can plot a graph of F against E and determine the gradient. The gradient will give you your Young's modulus, which is basically this. E is equals to gradient times L over pi over 4 d squared. Okay. So the quantities that you have are actually this. Find out D, find out L, find out F, find out E. Why do you need to make a few measurements, few different measurements to find Young's modulus? Okay, sorry, not why. They ask you to explain how a series of the reading, why a few different measurements, why is it that a few different measurements can be used to find the Young's modulus of steel? How? Okay, it's because you want to do this. So if this one is okay, then no problem. Okay, so I move on to the next part. Now we're going back into MCQ questions again. Okay, a known tensile force acts on a wire. The wire does not exceed its elastic limit. Which two measurements enable the strain of the wire to be calculated? Strain, they want the strain. Strain, you remember, is extension over original length. Okay, in the notes, I think I wrote it as change in length. Change in length is the general term. Extension is a more specific one because you know that change in length can be extension or compression, right? So it doesn't matter which one, just as long as you know that this one is either one of these two. Okay, so extension over original length, what are the two measurements that you need? The first one is obviously the unstretched length of the wire. The second one is the extension of the wire. Answer is B. And that is what you need. Okay, you want to measure those two, only then can you find the strain. Okay, okay, now for 21. The Young's modulus of steel is determined using the length of steel wire and is found to have a value of U. Value of E. Another experiment is carried out using a wire of the same steel, but half the length and half the diameter. What value is obtained for the Young modulus in the second experiment? Okay, now this one you will need to use ratio again. So the easiest thing to start with usually is this one. E is stress over strain, force over area, E over L, giving you FL over AE. Okay, so E is FL pi over 4 D squared. All right. What is constant here? Now, this is the equation that relates to both cases. So just now I mentioned to you, when you want to do something like ratio method to compare between two different cases, always find out the equation that relates both cases. In this case, the equation that relates both cases is this one. And then the next thing you want to do is that you want to find out what is the same for both cases. All right. So what is the same for both cases? You can actually do another experiment using half the length and half the diameter. Okay, so what do you think is constant here? There are some things that you can do. Okay, now you can assume that same F is used, even though here they didn't say anything. They just say another experiment is carried out using a wire, the same steel, but half the length, half the diameter. Okay, so what you can say here is that because this is same steel, that means it is the same E. Recall that in the notes, I mentioned to you that when it comes to Young modulus, under page 5 of your notes, Young's modulus is the same for any specific material, regardless of its size and shape. As long as it's the same material, it will always be same E. Okay, so when you look at this question now, they are made of the same steel, so same E. Okay, so you assume also same F. Okay, assume same F also lah, because here they say the experiment is carried out again. It's like saying they repeat the experiment again using same conditions, just that a different wire with different dimension is used. Okay, so here I will say that F okay, this one actually is a trick question. Actually, there's no need for me to calculate anything. The They want the Young's modulus, right? What is the value obtained for the Young's modulus in the second experiment? As long as you identify it's the same still, it's already going to be same E. No matter how experiment parameters are changed. Okay, so actually there was no need to do this, where I assume same E, same F, and whatever to do ratio. This one itself already tells you the answer. Same still, same E. So the Young's modulus that you get for the second experiment is just going to be E. Okay, there's no need to go through any long-winded process. As long as you see that there's a mention of same material, is same E. So just now, they didn't say anything about the amount of force that they use. I say assume that it's the same. Actually, I don't need to go through that process. As long as I see the same material, it's going to be same E. Okay. So this one answer is B. This is something like a trick question whose answer is very easy to deduce, provided you know what to look for. Okay, so 21 answer is E. So the 21 question 21, the answer is B. The Young's modulus remains the same as before. Then you go to the next question. The graph shows the variation in stress versus strain of a material as it's extended elastically. Why is the strain energy per unit volume of the material not the area under the graph? Okay, so take note of the term that they use here. They're asking you strain energy per unit volume. Why is it that the strain energy per unit volume of the material is not the area under the graph? Recall that I told you that strain energy per unit volume is area under stress strain graph. That means that in a graph of stress versus strain, like this, for example, it will be this. So what is wrong when you compare it with this graph? The question is saying that the area under this graph now why is it not the same as strain energy per unit volume? Notice that the only thing different between this graph and this graph is actually in terms of the axis. This one is stress versus strain. This one is strain versus stress. Okay, so while it's correct to state that strain energy per unit volume is area under stress strain graph, this one here is strain versus stress. Okay, the correct area to use should have actually been this. This area is the strain energy per unit volume. Okay, this is the correct one. This is the wrong one. So basically the question is asking you why strain energy per unit volume is not this area here. The answer is because the axes are the wrong way around. It should have been strain versus, so it should have been stress versus strain instead. Okay. So the other choice or answer, the graph is not a straight line. This one is wrong. The graph is strain stress instead of extension force. This is wrong. Material is polymeric. This is no longer in your syllabus. It won't be asked anymore, so don't bother about this. Polymeric is just a rubbery material. Rubber is a polymeric material. Okay. So B, C, D, op. The axes are the only answer is A, which is correct. If you're talking about area under the graph, which is this one, they ask you why is it not area, why is it not representing strain energy per unit volume? It's because the axes are wrong. It should have been stress versus strain instead. If you want to find the strain energy per unit volume given this graph, it should have been this area instead. Okay. So answer for question 22 is A. Okay. Okay, now going to question 23. A wire has a final length of 6 meters after undergoing a strain of 200%. What is the original length of the wire? Okay, bear in mind some of the wordings they use here. They tell you final length is 6 meters after going a strain of 200%. What is the original length of the wire? Okay, strain is extension over original length. Now, I can also say this, isn't it? Extension is the final length minus the original length divided by length, right? If let's just say that this one was my wire, original length L, once I put a loop onto it, the wire will extend like this. So I know I have an extension of E. Okay. So the final length is going to be this one. Okay. All right, sorry, maybe I make it more consistent before I draw here. Okay. So this is the original length. This is now the final length after the wire is being stretched, giving me this extension E. It's correct to say the extension E is the final length minus the original length, right? Okay, so I can also say that the question wants the original length of the wire. Because right now, if you try to use this, you have two unknowns. You know the strain, but you do not know the extension, and you want to find the original length. You have two unknowns. You cannot solve from this one. But if you change it to this form, strain is known, final length is known. This one is the only unknown. So you can solve to find the answer. Okay, so you're still using the same equation, but you just need to manipulate it a little. So since this one is in percentage form, remember to change it out from percentage form. It will be 200 divided by 100. The final length will be 6 meters minus L over L. So this one will be 2L, 6 minus L, then giving you 3L equals 6. Then L is therefore 2 meters. Okay, so answer is B. There you have it. Simple enough. The next question, the table summarizes some descriptions of evaporation. Which row of table is correct? So as I mentioned to you, anything that talks about states of matter, like or the processes in which they change from one form to another, this one is no longer inside your syllabus. Okay, so this one not in syllabus. Just omit this thing out completely. Okay, so that part is fine. Okay, now a force acts on a wire to produce extension E. The same force then acts on the second wire of the same material but half the diameter and 3 times the length of the first wire. Both wires obey Hooke's law. What is the extension of the second wire? Okay, now this one is the correct one where you need to use ratio. Okay, So, sorry. How do you go about doing this? It's something like this. E is equals to stress over strain. I'm just going to write it out quickly for you. E is equals to FL over AE. Sorry, this one is FL over AE, which will in turn be the same as pi over 4d squared times E. Okay, so this equation relates to both the cases here. Okay, there are two different cases. You want to find out what is the new value for the second case, the second wire here. For both cases, this equation relates to both cases. Then after that, what you want to do now is to find out what is the same for both cases. For the first wire and second wire, what parameter or what variable is the same? Okay. So what is the same here is that they tell you a force X on the wire to produce extension E, the same force is acting on the second wire of the same material. Okay. F is the same, E is the same. So I mentioned to you, if you have same material, it will be same E. So same force, needless to say, is same F. Okay, but this time is half the diameter and 3 times the length of the first wire. Both wires obey Hooke's law. One is the extension of the second wire. So here I can say that E and F are the same. Yeah, let me just make things a bit simpler first. Because I want to find the extension, right? I make extension the subject. E is actually FL pi over 4 d squared times E. Okay, I just switch the E's around. Okay, so now I will say that F and E constant. So this one constant, this one constant, pi over 4, needless to say, is also constant. That will mean that E is proportional to L over D squared. Okay, so this is the new relation you have. L is proportional to D over L is proportional to L over D squared. So now you have two different ways of doing this. I'll show you the two different ways. So right now you see they say it's half the diameter and 3 times the length. Okay, so if your diameter reduces by 2 times, that means your E will increase by 4 times because there's a square term here, you see. If your D reduced by 2 times, your E should increase by double the amount. Sorry, by a square. Okay. If it changes by 2 times, it will change by 4 times. If it changes by 3 times, it will change by 9 times for the other corresponding variable. So since the D reduces by 2 times, the E will increase by 4 times. This is the effect of changing D itself. But what about the effect of changing the length? Length here increased by 3 times. So since E is directly proportional to L, that means E increased by 3 times. So therefore, overall, E increased by 12 times. Because this one increased 4 times, increased 3 times, 4 times 3 is 12 times. Okay, so here I will say that my overall extension increases by 12 times, so therefore it's 12E. This is just you looking at this itself. What if I try to use a different method like the one where I actually try to calculate it out? Because E is directly proportional to L over D squared, I can say this. E2 over E1 is going to be the same as L2 over D2 squared over L1 over D1 squared. So that eventually I get this E2, E1 L2, L1, D1 square over D2 square. Okay, so half diameter would mean D2 is half of D1. 3 times the length would mean that L2 is 3 times of L1. Okay. So if I sum in everything here, what would I get? I will get 3L1 over L1. And then this one, D1 square, would just be D1 square. And then D2 square will be half of D1. Remember to square the whole thing. So eventually you'll see that L1 will cancel off. D1 square and D1 square will cancel off. So it's actually going to be 3 divided by 1 over 4, giving you 12. So E2 to E1 is 12. E2 is 12 E1. And E1 itself was actually E. So it's 12E. You can make the same answer as the one you see here. Okay, so you have two different ways of doing this. Either you do this or either you do this. Frankly speaking, this one is actually faster, the most straightforward one. But this one here is actually the most tedious one. So it really depends on which one you are more familiar with. Okay, personally, I'll use method number 1, but some people like method number 2. Okay, so just choose whichever you like. Okay, so that part is okay. All right, so the last thing here, yeah, it's already 4 p.m. So I think I better just stop here. Okay, now maybe I just do one part here for question 22. Which statement about elastic deformation and plastic deformation is correct? The answer is just D. Okay, elastic deformation is reversible, but plastic deformation is not. Elastic deformation is reversible because your material goes back to its original length. Plastic deformation is not because you return permanent extension, permanent deformation. So that is elastic and plastic. No? Okay, so the rest of it, this one, the answer A, B, and C is not entirely correct.